So, hello, everyone. As networks get faster and faster, we sometimes have the problem on how do I look at all the packets in my network if something goes wrong. Our next speaker is working at the Amsterdam Internet Exchange, and he's been working on some really cool device. He will present us now. So it's a pleasure for me to introduce Mr. Arjen Wijn.
Thank you. This presentation is made at the last minute during the network troubles, so please bear with me. And it's divided in three parts. An introduction part on what is an internet exchange, the place where I work, where I'm using this system or planning to use this system. Which problem needs to be solved by this system and the solution for that issue. I'm giving some real-life examples, which I hope I can interact with you. And then a solution which consists of a system that is not made for what you want to do with it. First, I'm going to tell a bit about what's an internet exchange, because even people that work in the internet industry sometimes don't have it right, in my opinion. And therefore, I present this tier model, where you on the top you have tier 1 providers that are big companies with large networks that span a large part of this world, but not the entire part. There's no company that has a network all around the world. And tier 1 providers, in the definition of Bill Norton, are providers that can exchange traffic with each other only by peering. And peering means that they see each other as equal, and that they don't have to pay to exchange traffic. So if this ISP wants to send traffic to this ISP, it can over this link, and they don't have to pay for it. Smaller ISPs, like the ones you probably have an internet account with, are here at the bottom. And they have to reach the entire internet. And they do that via an upstream provider, in this case, ISP E. And they have to pay a large amount of money for that, for this traffic that goes over this link. And all these smaller providers where you have your internet account, well, they are sort of close by to each other. So it makes sense that they exchange traffic with each other. And by just setting up a switch in the middle, like here, and connecting their BGP routers to that switch, they can exchange traffic. And by doing this, they offload traffic to their upstream provider, and for that, they save a large amount of money. And this is really a large money saver. And by the switch part, everybody that connects to this switch can exchange traffic with each other. They can peer with each other. They see each other as equal, and they usually don't pay for that traffic. They pay an amount of money to run that switch park for the internet exchange, but they usually don't pay money for the traffic. So, by connecting, everybody can talk to everybody, but that does not happen. Some people don't want to peer with each other. So, you don't have a full mesh of traffic exchange over an internet exchange, but some internet exchanges like the one I'm working for, it's quite common for people to peer with everybody that wants to peer with them. So, this switch park, this is what I'm babysitting in my life. That's there in the middle of all these providers that do all their own stuff. And they are really different. You have large providers with change management processes, and if you call them, you have to go to several layers before you get somebody who knows what you are talking about. And if you call another one, you hear his wife complaining and his kid screaming on the back. So these are very, very different cultures, and you can imagine that, if there is a problem between the connection, that you cannot really trust what one party is saying or what the other party is saying, because everybody has a different perception of the problem. And for that, we need to monitor the system. And monitoring can be done, and we do that by just plugging in a computer to the shared medium, to the place where everybody is connecting to, and look at the traffic that is being broadcasted, being flooded out of this switch. And that tells a lot. That tells really a lot already. And this is what we do all the time. And I'll give you an example of a problem that has been solved by this method. Well, not completely solved by this method, but for a great deal completely solved by this method. And on a Saturday, it's always on a Saturday, there was suddenly a huge amount of Ethernet multicast traffic coming out. Ethernet multicast traffic is flooded to all ports in the switch. And this was really huge. Even gigabit ports were saturated by this traffic, because the source of this was a 10 gig router. A 10 gig router that was sending Ethernet multicast to the shared medium. And by just looking at that packet, in the frame itself, there was typically IP unicast traffic. So this was really wrong. So the first idea is, this switch is wrong, right? We should close this switch, and we did. And that solved the problem. But was this really the problem? What do you think? Of course not. Just by looking at this broadcast traffic, we could see that just before this started, there was an ARP request. An ARP request that was not coming from a totally different router to a totally other different router. And this was that ARP request. I changed the source MAC address a bit and the IP addresses a bit, but this was it. And what is wrong with this? Can somebody tell? That's normal. That's normal. The ARP request is from a router that is saying, hey, I want to contact this. Who is this? Who has the MAC address of this machine? Please? Source is different than the subnet. Sender. No. What is wrong with this? The 195.69144.0/23, that's the ARM6 prefix. This was really true. Correct. Ethernet multicast is being recognized by the first bit in network order. If that's a 1, then it's Ethernet multicast. Then the switch knows, hey, if there's 1, I'm going to flood it all around. And apparently, this router from AS1, saw this address, and the implementation of this router followed the suggestion that is in the RFC that if you see a MAC address change, just change your ARP table. And the implementers of this router didn't think that somebody could send a multicast address there. Or it might even have been done by design. So, indeed, this 0 caused all these problems. So, then you think, the sender of this ARP packet, he is doing something wrong. He is making this multicast. And that is this router. So we were looking at this router. And then, well, you have to see, if that is really that router that is causing this problem. So the only way to do that is by looking at the traffic that is coming in. And we do that. And if there's a gigabit link, then it's technically not so much of a problem to look into that line. But yeah, it turned out that it wasn't this line. It turned out that there was packet corruption going on in our own equipment, flipping exactly this bit sometimes, causing trouble. So this guy was not to blame, this guy was not to blame, we were to blame. And this is an example of where you need monitoring in this internet exchange. So I'm here in the middle, and if somebody sends something with tuddle and it comes out as buddle over this line, or presumably over this line, I need to check it. And for that we need a monitor system that can look into the line. And it can either look here, or it has to look here, or it has to look at somewhere in the switch park. And, well, the switch park is all connected with 10 gigabit lines, multiple 10 gigabit lines. We now even bundle 8 10 gigabit lines to handle the traffic load. I'll give you another example of where we need monitoring, and this is also a real-life example. And first I'm going to give you a bit of the situation of how people connect. Routers are expensive devices, and then their interfaces are very expensive. So what do ISPs that want to save money? They don't connect that router directly, no, they connect the switch. And make one link to that router, and do VLANs over that link, which they can use to connect to their own network and to their transit provider. In this way, they save interfaces. With connecting a switch to another switch, where this switch is under another control management, then this switch is a potential really dangerous situation. Because switches, they just want to forward traffic, and they want to say, hey, I'm a switch, and they do all kinds of things wrong, and you need to configure them before you can do this. And not everybody does that. And it gets even worse. If two of these providers do this, and they say, hey, we are next to each other, let's offload some traffic from the internet exchange, because that port costs us money as well, you can see you have a potential loop here. And Ethernet does not have any loop prevention. Ethernet, when an Ethernet packet is going into a loop, it loops forever until you break it. There's no TTL like IP has that counts down to a number when it's being thrown away. So people do this, and this actually, especially when this all started in 2001, 2002, this brought our internet exchange down several times. Because sometimes people forget to do write mem, and the switch reboots, and it comes back in a state where it's not configured, or it's really looping, or it's even can loop behind that and sending packets into the shared medium with a high packet weight. That's bad. So we came up with a solution. We only allow one MAC address, because whatever you put in between our internet exchange and your router is up to you. But we only want to see the MAC address of your router. And if we don't see the MAC address of your router, we'll block it. And we can even close your port if you do that. But then, well, if somebody has a router there and it comes for some reason another MAC address there, we block it and we close the port. And we have a syslog message saying this is the source MAC, and often people say, I don't know that MAC address. Help. And for that, we need to monitor in this port as well. And this is a real-life example of a bug of just a router that was connected directly without any equipment to the Internet Exchange and was being shut down because it was sending packets from a VRRP MAC address that does not belong to on an Internet Exchange, but it was doing that. And well, from the syslog we could see that it was a VRRP address, but the guy said we don't run VRRP on that port, we run VRRP on the other side. So the VRRP process in this router was the usual suspect, but only by providing the router vendor a packet capture of that frame, we could tell them, hey, it happens when somebody is pinging to that router. And when somebody is pinging to that router, it also sends VRP on another interface, the reply, the echo reply. The destination address was a unicast address, so we could not see that by looking at the flood traffic. So here again, we needed to have a monitoring system that is looking into the line. So how do we do that on 10 gigabit Ethernet? Well, the first thing that comes to your mind is use a mirror port. Take another port on that switch, put some equipment on, like a general purpose PC with lit PCAP on it and TCP dump and stuff, and copy the traffic that comes in or out of that port to this mirror port. Well, 10 gig ports are expensive. That's one thing. It's a rare. The switches don't have that many 10 gigabit ports. We now have switches that can do up to 64 ports. When I started with this project, he had only switches that could do 32 ports, and then they were all in use. That was one of the problems, the port density. Another problem is the switch has to replicate some traffic. It has to split that traffic somewhere out. And this is a schematic picture of the input train of the switches we use. What you see here is there's the MAC chip, the optic, that is the interface, the optical interface, the MAC chip, the framer, the packet processor, and what they call the traffic manager. That's one line where the traffic is going through. And that's a 10 gigabit line. And for some reason, the vendor of this switch decided that the mirror port feature should replicate in the traffic manager. So basically sharing a 10 gigabit resource in that switch. And so if you enable the mirror port, you will have its bandwidth. If the bandwidth is bigger than 5 gigabit per second, you have packet loss when you turn on the mirror port. And that's not cool. Even outbound traffic is also copied there, so you divide your bandwidth by, you have 1/3 of your 10 gigabit bandwidth. So that mirror port option is tricky. It's tricky to use. And then you can say, well, who's using more than 3 gigabit? Well, we have guys already saturating 10 gigabit ports. So this mirror port is not so much of an option. But at the Amsterdam Internet Exchange, we don't connect 10 gigabit routers directly to an Ethernet switch anymore. Meet the fiber switch, the optical cross-connect. This is a really cool device. The only uncool thing is that it doesn't have that many blinking lights, but it works like this. It's a container with very, very dry air, with fibers that go into there and really positioned very, very precise into a lens array. And light coming out of this fiber is reflected on moving mirrors, reflected to a fixed mirror, reflected back to another moving mirror, and pointed into a fiber again. And by wiggling these mirrors, you can put the light from one fiber to the other. These mirrors make really, really tiny movements. Please, do you hear a question? Oh, sorry. So we have these devices in the middle. And we do that for redundancy reasons. Switches are not so much, so very reliable as well. 10 gigabit switches are really new technology, and this new technology, we know from experience, is not stable. So, and this fiber switch is a very simple, although it's very high-tech to move this mirror is very small, it's a very simple device. It just reflects light in and it reflects light out. It doesn't have any forwarding tables, it doesn't have software, it doesn't have chips that needs watts and watts of energy. It has just these mirrors that needs to be maintained in position, which is difficult to do, but really, really reliable. And we're going to use this switch for monitoring as well. We bought it to have redundancy, to have 2 Ethernet switches instead of 1, and then this reliable, simple device in the middle. And we're going to move that, and moving these mirrors also causes a little error. It causes a little link flap. And I thought that was interesting for you guys here at Chaos Computer Club, which are also concerned about privacy. That means if we are going to use this device for monitoring, we cannot do that unannounced. We always create errors on the port. So what we did by monitoring was using a traffic analyzer that is capable of monitoring at 10 gig per second. And this is a really expensive device that we use in our lab to generate traffic. But it can also capture traffic. It does not do that very handy, but it can. It can also act as a repeater, so you can put it in the line. So we use this photonic switch to use the traffic from the router going into that traffic analyzer, capturing the traffic and forwarding it again. And by that, we now, and we then monitor the traffic. But this is not a really handy device to do that, because the traffic is being copied into maximum of 256 megabyte of memory, and then you have to stop it, or it's being flushed through that memory, and taking it out of that memory and then analyze it. You cannot look at this in real time. And so you have to set filters to do that. You have to set triggers to get what you want. And sometimes when you are troubleshooting, you don't really know what you are looking for. So we want to have a general purpose PC, just like we do with the 1 gig and the 100 megabit lines. But on 10 gigabit, you can't buy a PC for that. 10 gigabit has an interframe gap of 9.6 nanoseconds. You only have a few clock cycles in a really fast PC, or a few hundred, to do something with that. That's way too less. So, what's the solution? The solution is to look for special dedicated hardware that runs on a general Linux PC where we can use our lib tools that are built upon libpcap, and that's doing just the same as we do with this traffic analyzer. And we found such a card. It's a card that is originally made by Meta Networks and is now there's a company that's now bought by 410 Networks. And Meta Networks made it really for security purposes, to make an IDS or IPS system that is capable of looking at of doing IDS at 10 gigabits per second. It's, if you will, snort in hardware. And how does this card work? Well, this card, wait a minute, has 2 10 gigabit Ethernet optics, XPEG optics. It has a chip that is doing the forwarding between these 2 optics. And the traffic that is exchanged between these two optics is being tapped to another programmable chip that is filtering it out. And the guys from Meter Networks made software that take Snort's rules and make that into an FPGA bit stream. So you have the Snort rules, and it's being converted into all kinds of logic, filtering, looking at the patterns you are interested in, and only copying the packets you are interested through to the PCIX interface, which goes to the PCIX bus of the computer. Then it's talking to a driver, and from the user perspective or from the software perspective, that's just a normal Ethernet interface under Linux. And you see it's quite a reduction of traffic. Here you have 10 gigabits per second, that are 14.8 million frames per second at the max. This does all full 10 gigabits per second. And here you have a maximum of about 600,000 frames per second, which you can use your software on. So I thought, hey, this is a device which might help us with monitoring traffic. And Meter Networks was a really open source company, so they said, okay, here's our software for this filter, and here's the software for the drivers, and go ahead, do what you want with it. Unfortunately, Force 10 is not an open source company, so we're now a bit of doing things our own now. But let's see further on this device. It consists of two Xilinx FPGAs, the front end and the back end. It also has a lot of static RAM, fast memory, which is used in the IDS purpose as for stateful inspection and to hold fragments, to reassemble the whole packet once all the fragments are in. The front end FPGA, an FPGA is a chip that needs a program to function. It doesn't hold that program. It's at startup, at boot up, being programmed by a program that is being stored in this flash memory. And this flash memory can be reprogrammed via a JTAG interface. You really have to plug your JTAG interface onto the board to do that. Same goes for this CPLD that holds its program in itself, but you can also reprogram it if you want. This CPLD is containing, I think I never looked at it, just containing PCIX bus software from Xilinx, and it's not really that interesting. This FPGA this is the heart of the system. Here is where the filtering takes place. So and together with this FPGA, those are the interesting parts. So let's look at this top FPGA, how that's being built. Well, it consists of two XAUI interfaces. XAUI is a standard interface where the XPEC connectors are connecting to. And this piece of software in the FPGA you can just get from the maker of the FPGA. So that's what really happened. And those are just connected together, but because of this is also an intrusion prevention system, they put some gates in between to block the traffic if you want to block it. And that means that the traffic is really being cut off. It's a cut-through switch, if you will. Frame is coming through, and if the IDS system says, hey, I want to block this traffic, it's just being cut off. So you get an error on the receiving side that there is some broken frame coming in. And of course, it's being tapped. For the IDS system, there is also a block in between. A block in between this and this block that is normalizing URLs and stuff. That's really something that Force 10 doesn't want to give to me, and I'm also not really interested in, because I want to use it as a monitoring system, and anything that changes the packet is unwelcome in this system. So that's why I didn't draw it in. The Zowie interface is 64 bits wide, and here there is a converter that puts these 64 bits into 128 bits and halving the clock rate with that. And that is just being copied through to the backend FPGA. And from the backend FPGA, you can get the signal to block the traffic. So let's see what we get then from this FPGA. We get a 128-bit word with the entire frame. This is the first word you get, completely with the preamble. Ethernet starts with the preamble of 10101010 or 5555, if you will. And at the end, there is a special bit pattern to say, hey, now the Ethernet frame starts, and it starts with the destination MAC address. But then you also have 16 bits over, so here is the first part of the source MAC address. And if you remember that we are particularly interested with this last example in the source address, you see this is what we're interested in. And then you get more. You get the rest of the frame, more and more and more, until the last piece of the payload, and then it starts over again. You get the next frame. And for IDS purposes, this is fine. Your IDS people are interested in the payload. They are interested in bit patterns that are there that assemble attacks. But we are mostly interested in this kind of headers and in the source MAC address. And the first problem I encountered with this IDS system is that they didn't really care about this. So all the counters in the system, they didn't work with this word. To change it, so this piece of data could be used. And that restrains your timing as well, because here they could do all kinds of things. While this was coming in and they didn't do anything with it, well, I'm particularly interested in that. But there was enough resource, enough timing to do that. So what happens in the backend FPGA? The backend FPGA is so-called single data multiple instruction system. There was this guy called Flynn that in the 70s made a taxonomy saying you can have one processor with one set of data that's doing its job. In the 70s and early 80s, you had this, well, the home computers and the PC that were doing this. This PC got data in, was processing it, got data out. Then there came the superscale processors like your Pentiums and stuff that can have multiple data and multiple PC, dual core and that kind of things. You can also have a CPU that does one instruction on multiple data. Examples of that are graphical processors that get one instruction and different processors do different pieces of the screen. But this is a system that uses one piece of data and applies multiple instructions on that. And that's not really common. But for this purpose, it's really suitable, and especially for the IDS purposes, it's really suitable because you have a huge amount of patterns you want to match. And if you make all these little tiny processors that match this pattern and work all together on the same data, you can make a really fast system that compares this data. And well, this is how the Force 10 P10 is really working. All tiny processors that compare a pattern on a small piece of the same data. And what this system really does is, on compile time, putting these rules in. And by that, sharing between different rules, different components, different resources in that FPGA. And this is how they can get so many rules into one FPGA. But for troubleshooting purposes, like we want to use it, that's not really a good approach, because troubleshooting is by definition dynamic. You don't know what pattern you want to match against until you know what you want to do. With security, you have tons and tons of known attacks you want to match against, and you can compile that into an ideal set of ideal bit stream that you can put into your FPGA. So what I did is making these things dynamic. You can put patterns into these registers from the host PC to these tiny processors. Another thing was that these processors were really made for IDS purposes. They could not match on something that was not there. They can only match on something that's there. And it took me a while to figure out, hey, an IDS system is about matching patterns. It's not about not matching patterns. And remember this, not this source MAC address. For troubleshooting, you really want to match on something that is not there but should be there. So a not operator has to be built in. It's not really difficult, but it wasn't there. I didn't tell how this thing is working. So here in this register, there is a pattern. Here, this is this 128-bit word that is being copied into this processor, and it's being compared with each other. And if it fits, and it also fits the offset where it should be, then, well, this is being 1, and your whole rules together make that the frame is being copied to the PC or not being copied to the PC. I hope this is understandable. So, I explain it here a bit better. So we have this source MAC address, and on the first word we match in register X the pattern of that piece of the MAC address we want to match against. Then the second word comes in. For that we need 2 of these processors, if you will, to match it against. One processor matches 16 bits, and that together with the first matching makes that you can really look at filter traffic you are interested in that is coming by with 14.8 million frames per second. And to do that, Meta Networks made what they call an API. Basically, it's a description of the signals that are there in the FPGA and building blocks that they have, which they call the memory management. That is for the SRAM. The packet processor that's really making this, really processing this frame that's coming in and does some basic counting. And some signals from the front-end FPGA and some signals from the host. And a signal to capture the match memory, and also a signal to block frames, if you will. And it's just a description, nothing else. You have to make your own functionality there in either Verilog or that other language. I forgot. So, working with this, I thought, hey, you can make a counter. Just count frames, because we can only capture 600,000 frames per second to the PC, and that's already a lot. But sometimes just counting an event just helps, and so we made a counter. And of course you can make multiple counters, so you can program different events that are going on. Another thing is that this counter is resettable, so If you are really looking for a problem and you see this counter counting up to a zillion, you want to say, is it now over? And you don't know, so you can zero it and then see if it comes up again. That's a really handy feature. Sometimes you don't know what you are looking for. The traffic is way too high to capture, so it was also handy to make a sort of random sampler that is just taking frames out randomly out of the stream, copying it to the PC, reducing the data rate, a bit like slow is working as well. And that consisted just as a frame counter that controls a random number generator. Actually, the random number generator is constantly making numbers. And once the frame counter counted one up, it's copying that random number into this register, and it's just compared to that next frame counter, and that makes that there's a sample going out. I haven't really used this feature, but it might be handy in the future. It was easy to program. Another thing is, on troubleshooting, you also want to look at frame checksums, or not really frame checksum, but checksums in the IP header, or checksum, TCP checksum, or ICMP checksums, or UDP checksums, just to see if this tunnel is being changed in buddle somewhere. That makes that the frame checksum doesn't match. And this turned out to really, really hard one, because that force-10 system is giving you frames in all kinds of words, and then suddenly you get a new frame. It doesn't tell you, hey, this is the end of the frame. And TCP and UDP checksums and ICMP checksums are really calculated over the entire packet. So your packet is there, you can calculate your checksum, and then you say, hey, this was the packet I'm interested in, but it's already gone. I didn't solve this solution yet, didn't solve this yet, I have any idea on how to work on it. One thing could be using the length field. Yeah. But the length field, I think it's kind of dodgy solution, because you work with the data, you use the data that you want to work with. So the solution is probably in the front end FPGA where you know where the end of the frame is. And then you also know that you might have a frame that's too long or a frame that's too short, and you can trigger on that as well. And this is actually where the project is right now. A future solution, future wish, is using this SRAM memory. Because remember this example 1 where we had one frame before that was actually causing the problem that you were looking at. So it might be handy to store the different frames coming by, and then have a trigger and have the frames before that, basically looking back in time. For that, this SRAM is a handy resource to have. But the problem is that the API from force10 really doesn't describe how this SRAM is working, and I have to reverse engineer that part, unfortunately. So this is where the project is now, and we still have 15 minutes left, so there's a lot of time for questions. A question there. Can you please wait for the microphone?
You said that the main processor contains these snort rules. I realize that you may not be using those at the moment. Is it just the rules, or is there any pre-processing done? Because I would think that would really interfere with your monitoring if the preprocessors were being used before you actually looked at the package.
Yes. The preprocessor is. I didn't draw it. It's here. It's before it's being converted to 100 and 28 bits. There's a preprocessor there, and that's really interfering. So at first I asked Meter Networks to bypass this whole thing, and they did. Now I also have the code for that FPGA and without the preprocessor. So that's not doing it. The rest is not interfering with any data. The snort rules itself are all in the backend FPGA. And well, I don't use that snort. I even never used it as a snort box. I don't know how that works actually. So does that answer your question? Yep. Okay. Any other questions, please? Yes.
Okay. On the calculation of CRCs for IP packets, if you've already discarded the earlier packets that were captured, you don't have them around to calculate the CRC for the later halves. But you could maintain a partially calculated checksum. And if you have enough data to like match it up so that you recognize it with the later fragments that come in.
You say you can calculate the checksum partially.
Yes.
But you need to match it against a checksum that is in the packet.
Right. Yeah.
So I don't really understand how to do that. You have, let's say, one as checksum in your packet, and then you calculate and you come at 0. But it might be that this fraction you have left that you cannot calculate right now, makes it 0 again. Makes it 1 again. And then the packet is good. So I don't see how, if you can tell me how I can partially calculate a checksum, then I'm really interested. I don't know.
I mean,
what I can do is, and actually did, I can calculate the IP checksum without option headers. Because just the IP packet alone is, and the Ethernet frame is too small to match the minimum of 64 bytes. So I have some padding bytes left to do the calculation. IP is possible. IPv6 doesn't have a checksum, but you basically are more interested into this payload data, that is this, where you have much more chance to have a bit error in. And that is being calculated right at the end of that frame. And the problem is that I don't know where the end of the frame is. But if I can partially calculate, I'm really interested. I'm not so smart to do that. You have?
Yeah. The two XenPacks or whatever it is are used.
XPack.
XPack, okay. You use the end is used and the other components probably also active. So if the power fails on the box,
then
the link is dead?
Then there's no forwarding.
Okay. Do you use other mechanisms? Because I guess that customers don't really like you. Well, probably they already have a problem when you put the box in between, but...
Yeah. It's not really not meant to be permanently into the line.
Okay.
At first, we are not using this as for any lawful interception, whatever. It's not happening at the Internet Exchange because you have...
Okay.
It's just to put into the line, to look at the traffic and getting it out again. The photonic switch that we use to do that,
it copies the data already, right?
Is also an active device. You have photonic switches that are basically relays that relay fiber, but these are these mirrors that are being held into position by static electricity. It also needs power. The Ethernet switches also need power. So the solution here is use redundant power. And another thing is that many ISPs have their own redundancy solutions. You can have two connections at one internet exchange. They can use M6 and D6, whatever.
Yep.
And so.
Hello. My question is regarding WAN-Fi and LAN-Fi. I believe your switch vendor supports both. Does this solution support you doing the same thing with WAN-Fi configurator?
We don't support Wi-Fi framing at the M6. We only do Ethernet framing.
Well, that's still Ethernet framing, but okay.
And there are no Wi-Fi is not a framing, right?
Well, you instead of doing 64B66 framing, you do STM64 framing. It's still Ethernet frames. Well, okay,
Yeah,
it depends on how you define Ethernet
Yeah,
framing.
but we only look at the plain Ethernet frame, preamble, starter frame delimiter, MAC addresses. This is what we see, and we don't support any STM1 or other type of connection.
Okay, I'm not talking about packet over SONET. I'm still talking Ethernet, but
What's that?
it's framed so it's compatible with STM64, but it's still Ethernet. But okay, your answer is no. That's what I was looking
No,
for.
and also this XPAC optics that are on this thing, yeah, that's just only Ethernet framing.
Well, yes. For instance, your Ethernet switches, I know for a fact, can be configured for WAN-Fi, LAN-Fi on the port. So it has a dual mode framer that will do this. So my question was this, if the XPACs, I don't know if the framer is on the XPAC like on the ZenPack, or if it's an XFP type.
It's on the XPAC. They don't do that.
Yeah, then that answers the question. Then it's not a problem.
We don't use it. So. More questions? Okay. Then I hope it was clear and interesting for you.